So we have seen the typical capacity of the MIMO channel, which is given by C is equal to maximize trace of RSS is equal to empty log 2 determinant over IMR plus ES by MT and not H RSS H Hermitian. So this is the typical capacity expression of MIMO channel that we have seen. So now we want to get some insights from this capacity expression. So we'll consider two cases. Case 1, when there is no CSI is available at the transmitter, and case 2, the CSI is available at the transmitter. Let us first look at case 1 where there is no CSI at the transmitter, but at the receiver side we are assuming that we have perfect estimation. So now from the transmitter side we are sending symbols S1, let's say S0 to S1 and so on up to SMT. So this we are transmitting from the transmitter side. So you can't do anything at the transmitter side, but one thing what you can make sure is that all the symbols they are zero mean. The covariance of symbols is equal to IMT and expectation of SISJ conjugate is equal to 0 for all I not equal to J. So that means what we are saying? We are saying that they are independent symbols. All the symbols they are equally powered and are independent at the transmitter antenna. So in that case, what we can do? We can basically see the RSS is identity. And now the capacity expression is log 2 determinant of IMR plus ES by MT and not HH Hermitian. Then from the video of statistical properties of H, we know HH Hermitian can be decomposed using eigenvalue decomposition. That means HH Hermitian can be factorized into Q lambda Q Hermitian, where Q is the orthonormal and lambda is the diagonal matrix that comprises of lambda i's of HH Hermitian. And again we have Q Hermitian is equal to IMR. So therefore we replaced HH Hermitian with Q lambda Q Hermitian. Then using the property of determinant of IM plus AB is equal to determinant of IM plus BA. Now in the previous expression we have Q lambda Q Hermitian. So if we assume A is equal to Q, that means this is A and this is B, then according to this property we have determinant of IM plus Q lambda Q Hermitian is equal to determinant of IM plus Q Hermitian lambda. So this is the most suitable form because we know Q Hermitian is equal to identity. So basically we can reduce the capacity expression to C is equal to log 2 determinant of IMR plus ES by MT and naught, and then we have lambda here, which is a diagonal matrix that comprises of lambda i's. So basically capital lambda is equal to lambda 1, lambda 2 and so on. Here we have 0 and non-diagonal elements are 0. So you have lambda i's here. Now for this particular diagonal matrix, what is the determinant? Determinant is the product of eigenvalues. So we have determinant is equal to product. So we can replace this determinant with the product I goes from 1 to R of this particular matrix. And then we know that log of product is equal to summation of log. So we can replace this with summation sign. Summation from I goes from 1 to r log 2 1 plus es by mt n naught lambda I. So this is the capacity of MIMO channel. So from here what we can see, the capacity of MIMO channel is the sum of r number of CISO channel. So what is this? This is the capacity of CISO channel. And then we have summation over R. So we have R number of CISO channels, and the capacity of MIMO channel is the sum of R number of CISO channels, where each have a power gain of lambda i's. Okay, so when we have MIMO, it becomes the sum of R CISO channels, and MIMO gives you the parallel CISO links. So we can simplify our diagram as follows: transmitter and receiver. So this is transmitter and we have receiver. So basically with MIMO what we can do, we can basically make a parallel CISO links. And how many links are there? Are such links are there, and each link with gain lambda I. Each link has a gain lambda I, with the transmitting power of each link is Es by Mt, and the noise corresponding to each of the link is N naught. So this implies that we have a linear growth in system, linear growth in capacity for such system. Now we want to find out what property of H would lead to maximum capacity. Okay, so what is the nature of H that maximizes the capacity? This is what we want to see. So we are given a fixed total channel power, square Frobenius norm of H. What is square Frobenius norm? This also we have seen. This is summation over all elements m and n, and then we have h m comma n mod square. So basically you have, for every element you take the mod square and then you take the summation of over all the elements, you will get square Frobenius norm, and this is equal to the trace of H Hermitian. For H Hermitian, it has lambda i's, and the trace is the summation of all the diagonal elements, and this is equal to Pt. Pt is the total transmit power. So now assumption is we have Mt is equal to Mr is equal to M, and we are assuming it is a full rank matrix. R is equal to M. Okay, so basically rank, we define rank of a matrix as rank is equal to minimum of Mt cross Mr, Mt comma Mr, and if both are equal to M, then rank is equal to M, assuming that all the rows they are independent. So then we want to maximize this expression which we have obtained in the previous slide. So here what you can see, you have logarithm of 1 plus lambda i's. Lambda i's is the optimizing variable which we want to find out, and the trace of all the lambda I is equal to Pt, means the total power should be equal to Pt, and lambda i's we want to optimize. So if you carefully look at this expression, this is like log of something, optimizing variable lambda I, and logarithm is a concave function, so you are basically maximizing the objective function which is a concave function, and when you solve this problem you will get solution as lambda I is equal to lambda j is equal to Pt by M. So what we are saying that capacity, this is the optimal solution. Okay, this is the optimal solution, and what we are saying that capacity is maximized when all the lambda i's they are equal, and this only happens when H is an orthogonal matrix, because when H is orthogonal, then H Hermitian is equal to H Hermitian H is equal to Pt by M I M. Okay, so now what you need to do, you need to substitute this expression in the earlier expression of capacity, which was in the form log to 1 plus H Hermitian, sorry, Es by N naught Mt N naught H Hermitian. You basically need to substitute this expression here in place of H Hermitian. So what you will get? You get Pt by m, mt is equal to m. So we have m here, and this will become m log 2 1 plus es by n naught pt by m square. So we have m outside here because it was like summation I goes from 1 to m log 2 1 plus es by mt n naught lambda I. This was our previous expression, but after substituting the value of, let's say, H Hermitian, you will get pt by m. Now this index, now this term is independent of the index I. So what we are doing, you are basically multiplying it with m, replacing the summation with m, because this becomes independent of I. So you get m log 2 1 plus es by n naught pt by m square. Now if we assume that each element of H has a unity power, then norm square Hij is equal to 1, and we get the square Frobenius norm is equal to m square. And what is square Frobenius norm? Square Frobenius norm in our problem statement, this is equal to pt. So basically you can replace pt with m square. So here you get m square, this and this will get cancelled, and you will get c is equal to m log 2 1 plus es by n naught. And this is the capacity of an orthogonal MIMO channel, which is m times the capacity of SISO channel. Okay, so what when we are saying that H Hermitian is equal to I, what does it implies? It basically implies that at the receiver side, if you have H11, H21, sorry, H12, H21 and H22, and if you multiply it with H Hermitian, and again you have symbol also here S1 and S2, if you multiply it with H Hermitian, this will become identity. So what you will get? You will get I into S1 S2. So S1 can be recovered easily without having any influence of S2. So this is the making of orthogonality. Orthogonalizing the channel means that signal transmitting at any one of the channels, they are not having any influence of any other received channel. So with this, so what is the capacity expression of an orthogonal MIMO channel? Which is given by m log 2 1 plus es by n naught, and this is the case when there is no CSI at the transmitter side.